Assalamualaikum everyone, I'm Sunjida Nova and today we are going to explore a fascinating question. What if I told you that two machines can do exactly the same useful work, but one of them can require much more current from the power supply? Why? The answer is hidden in something we call power factor, and once you understand the physics behind it, power factor stops being just another electrical formula. It becomes a story about voltage, current and timing. So let's find out why the same useful power can sometimes need much more current. Imagine two factories standing side by side. Both factories are supplied at the same voltage. Both factories are producing exactly the same amount of useful mechanical work. Both require 10 kilowatt of real power, but factory A draws about 44 ampere while factory B draws almost 87 ampere. Same useful power, same supply voltage, but almost twice the current. Why? Where is that extra current going? Is factory B doing twice as much useful work? If not, why does the transformer still have to carry that current? Why do the cables become hotter? Why does the voltage drop become larger? And how can connecting a capacitor near the motor reduce the current drawn from the source without reducing the mechanical output of the motor? All of these questions lead to one extremely important concept called power factor. Today, do not memorize power factor as simply power factor is equal to cos phi. Instead, we are going to understand what physically causes power factor, why voltage and current become out of phase, why induction motors normally produce lagging power factor, why poor power factor increases current, why higher current creates real engineering problems, why transformers are rated in kilovolt ampere, how capacitor banks improve power factor, and what power factor actually means in real electrical system. The goal of this lesson is not to memorize another equation. The goal is to understand the physics behind power factor. Imagine an electric heater. Electrical energy enters the heater and becomes thermal energy. There is a net conversion of electrical energy. Now let's consider an electric lamp. Electrical energy enters and is converted into light and heat. Let's consider a motor. Electrical energy enters the motor and some of it eventually becomes mechanical shaft output. Again, there is a net conversion of energy. The rate of this net energy conversion is what we call real power. Real power is represented by P and measured in watt, kilowatt or megawatt. For example, if a motor consumes 10 kilowatt, then electrical energy is being converted to a net rate of approximately 10,000 joule per second. So whenever you see kilowatt, think how fast is electrical energy actually being converted into useful output and losses. But a motor is not simply a resistor, and this is where the power factor story begins. Why does a motor need something besides real power? Look inside an induction motor. The motor contains electrical windings. The current flowing through these windings establish magnetic field. Think before we continue. Can an induction motor operate normally without a magnetic field? No. The electromagnetic field is fundamental to the operation of the motor. Therefore, the motor needs electromagnetic field energy in addition to the real energy ultimately converted into mechanical output and losses. As current builds in the winding, energy is stored in the magnetic field. When the magnetic field changes, some of this stored energy can return to the electrical circuit. Energy is moving back and forth. It is not all undergoing permanent net conversion. This oscillatory field energy exchange is associated with reactive power. Reactive power is represented by Q and is measured by volt ampere reactive, kilovolt ampere reactive or megavolt ampere reactive. Is reactive power useless? Students sometimes hear the statement reactive power is useless power. That statement is misleading. Think about a transformer. Can a transformer operate properly without alternating magnetic flux? No. Can an induction motor operate without magnetic flux? No. Therefore, electromagnetic field behavior is essential to many AC machines. The problem is not simply the reactive power exists. The engineering problem is that the current associated with this reactive exchange will have to travel through the electrical network. It may travel through the generator, transformer, feeder, cables, breakers, switchgear and motor windings, and real conductors have resistance. Therefore, even though some reactive energy is returned, the current associated with that exchange can still contribute to real heating losses in electrical network. The key concept is reactive power is not simply wasted power, it is associated with oscillatory electromagnetic field energy exchange. However, the reactive current still has to be carried by the electrical network. Why does inductance cause a phase difference? For an ideal resistor, voltage and current rise and fall together. They are in phase. Therefore, we can say that phi is equal to 0 degree. But an inductor behaves totally different. For an ideal inductor, we know V of L is equal to L times ddt of I. Look carefully at this equation. The voltage across the inductor does not depend simply on the amount of current. It depends on the rate of change of current. As current tries to change, the magnetic field changes. The changing magnetic field produces an induced effect that opposes the change in current. Therefore, for sinusoidal steady-state operation, current lags voltage in an inductive load. The displacement between voltage and current is represented by the phase angle phi. For a purely resistive load, phi is equal to 0 degree. For an ideal pure inductor, phi is equal to 90 degree. A practical induction motor contains both resistance and inductance. Therefore, its phase angle normally lies somewhere between these two ideal cases. The key concept is power factor begins with the physical behavior of the load. It is not simply an arbitrary number written on a motor template. Why does phase difference change real power? Let's consider the RMS voltage is V, the RMS current is I, and the phase difference between them is phi. For a sinusoidal AC circuit, we know P is equal to VI cos phi. Students often memorize this expression, but let us ask one more important question. Why does the equation contain phi? Why isn't real power simply VI? The current can conceptually be separated into two components. The component in phase with the voltage is I of P is equal to I cos phi. This component contributes directly to the average real power transfer. The perpendicular reactive component is I of Q is equal to I sin phi. Therefore, P is equal to V times IP. Substituting this equation, we obtain I of P is equal to I cos phi, and finally we obtain P is equal to V times I cos phi. The power factor, the factor cos phi, is therefore not simply a mathematical correction factor. It tells us how effectively the voltage current combination contributes to net real power transfer. Now, the power factor has a physical meaning. Power factor is defined by P divided by S. Here S is the apparent power. For sinusoidal voltage and current, power factor is equal to cos phi. Let's imagine that you are a transformer. Do you care about only the mechanical power produced by the motor? No. Your winding carries the actual RMS current. Your insulation experiences the applied voltage. Therefore, you must physically handle both current and voltage. For a single-phase sinusoidal circuit, we know that S is equal to VI, where S is the apparent power. Its units are volt ampere, kilovolt ampere, or megavolt ampere. This is one reason transformers and generators are commonly rated in kilovolt ampere rather than kilowatt. The key concepts of this is power factor tells us how effectively the electrical system's voltage current capacity is being used for the real power transfer. If power factor is equal to 1, then P is equal to S. But if power factor is equal to 0.5, then P is equal to 0.5s. For the same real power requirement, a lower power factor requires a larger apparent power, and that produces one extremely important consequence: more current, must flow. The equation that makes the engineer scared, P is equal to VI into power factor. Rearrange the equation we obtain. Current is equal to P divided by V into PF. Let's consider P and V remain constant. Then we can say that I is inversely proportional to power factor. That means if power factor decreases, I will increase. This is the practical heart of power factor. Suppose a single phase industrial load requires P is equal to 10 kilowatt from a 230 volt supply. Let's consider case 1. In case of unity power factor, we obtain I is equal to 43.48 ampere and the apparent power will be 10 kilovolt ampere. In this case, the power factor value is 0.5. P is still 10 kilowatt. If we put this value in this equation, we obtain that I is equal to 86.96 ampere and AC is equal to 20 kilovolt ampere. Notice what happened. The real power remained 10 kilowatt. The supply voltage also remained 230 volt, but the current approximately doubled. Therefore, we can say that same real power plus same voltage plus lower power factor is equal to higher current. Now the mystery from the beginning of the tutorial has an answer. Why is higher current such a serious problem? Suppose the original current flowing through a conductor is I, then the power loss as heat is P is equal to I square R. Let's consider for some reason the current doubles. So the new current become I is equal to I new is equal to 2 times I. What happens to the power loss? We simply put twice I into our main equation, then we obtain power loss is equal to 2I whole square into R, and it become P loss is equal to 4 into I square R. But remember, the original loss was I square R. So now power loss is 4 times than before. That means something very important. Double the current and the I square R losses become 4 times larger. And this is why higher current is such a serious problem. More current means more heating, more energy wasted in cable and equipment, and potentially larger conductors and electrical components are needed to handle that current safely. So power factor isn't just about a number on a meter. It can directly affect how much current flows and therefore how much energy is lost as heat. This is why poor power factor is not merely an academic problem. Higher current can cause increased conductor heating, increased I square R losses, larger voltage drop, poorer voltage regulation, increased transformer loading, large cable size requirement, increased generator loading, large switchgear requirements, and reduced available network capacity. Let's consider a transformer that can safely carry only a certain amount of RMS current. If a large portion of that current capacity is occupied by reactive current, less current capacity remains available for additional real power loads. Therefore, improving power factor can effectively free useful transformer and feeder capacity. Now return to the mystery from the beginning. Two factories require the same useful real power. Why can one factory draw much more current than the other? Because the factory with proper power factor requires a large apparent power for the same real power demand. Therefore, its source, transformer, cables and switchgear must carry more RMS current. The difference is not necessarily in how much useful work is being done. The difference is in how effectively the electrical system's voltage current capacity is being used for real power transfer. That is what power factor tells us. Remember the physics, not just the formula. Now return to our factory one final time. The motor turns the pump that requires real power. The motor also needs an electromagnetic field that introduces the reactive behavior. The transformer and cables must carry the actual voltage and current demanded by the system that give us apparent power. And power factor tells us how effectively that electrical capacity corresponds to real power transfer. When the power factor becomes poor, more current may be required for the same real power. More current means more burden on the electrical network, and because P loss is directly proportional to I square, that additional current matters enormously. Then engineers install an appropriately designed capacitor bank near the inductive load. The motor still needs its magnetic field. The motor still performs the same useful mechanical work, but the capacitor provides the opposing reactive compensation locally. The net reactive power burden seen by the upstream source decreases. Therefore, if Q decreases, which causes S decrease at approximately constant voltage, I also decreases. As a result, the power factor increases. So the next time someone writes power factor is equal to cos phi on the board, do not simply memorize it. Think, why is there phase difference? Because inductive and capacitive elements store and return electromagnetic field energy. Why does low power factor matter? Because more current may have to flow for the same real power transfer. Why is that additional current a problem? Because it increases conductor loading, heating, voltage drop, and I square R loss. And finally, why can a capacitor improve power factor? Because its capacitive reactive behavior opposes part of the inductive reactive requirement and reduces the net reactive burden seen by the upstream source. Now, the entire concept in 4 questions. When you hear real power, think where is electrical energy undergoing net conversion. When you hear reactive power, think about where is electromagnetic field energy being stored and returned. When you hear about apparent power, consider how much total voltage current loading must the electrical system handle. And when you hear about the power factor, think how effectively is that electrical capacity being used for the real power transfer. Final memory map. Real power means net energy conversion, unit watt, kilowatt or megawatt. Reactive power means field energy exchange. The unit is volt ampere reactive or kilovolt ampere reactive or megavolt ampere reactive. Apparent power, total voltage current loading. It can be represented as the unit volt ampere, kilovolt ampere or megavolt ampere. And finally, power factor is equal to P divided by S. Tell us how effectively apparent power capacity is being used for the real power transfer. One final message for all of you. Power factor is not merely a number between 0 and 1. It tells a physical story about energy exchange, phase difference, current, and how effectively we use the capacity of an AC electrical system. Once you understand that physical story, the equation becomes much easier to remember. Why? Because you know where they come from, why they exist, and what they physically mean. Do not memorize power factor, understand the energy and current behind it.